Great. Yeah, thank you very much, Regula Meyerhofer, for this kind introduction. And I don't think I have to say anything more about ISOE, the Institute for Social-Ecological Research, a part of the fact that we are dealing with all kinds of sustainability problems and try to find solutions for these kinds of societal problems, what we call crises of societal relations to nature. And we do this in all kinds of fields, for example, in the field of biodiversity, more a classical area of sustainability research, but also in the fields of sustainable mobility or everyday use of energy and the like. And two of our research units deal with water, and one is dealing with water resources and land use, so focusing more on the natural side of or the resource side of these issues. And I am in my research unit focusing more on the question of infrastructure, as has been introduced so kindly already. So I will repeat or tell you the title of my talk: Success Factors and Challenges of Water Reuse for Agricultural Irrigation in Central Northern Namibia. And I will give you a broad overview over what is going to come within the next 30-40 minutes. And I will present to you two case studies of our research projects in the past on water reuse in Namibia. So the one is the Kuvu Waters project, and the second case study is the Epona project. And then I will conclude by trying to integrate that into a broader framework of what our current research is about before I conclude with some ideas on what are the lessons learned and the success factors from our perspective. So first of all, where are we? So we are in Namibia. First of all, Namibia in terms of where is it in a geographical scale. So it is in southwest Africa. So it's bordering Angola in the north, Botswana in the east, South Africa in the south, and the Atlantic Ocean in the west. So this small map shows you the location of Namibia in Africa. And we are focusing on central northern Namibia. So this bigger map shows you central northern Namibia. One thing that you might know already is the Etosha National Park, a salt pan which can be visited by tourists and the like. And our pilot plants for all kinds of water-related projects and technologies are here north of the Etosha National Park, and the pilot plants for water reuse are in Utapi, very close to the Angolan border. Some facts and figures on Namibia in general, but also on the location itself, Utapi. So first of all, there are no rivers within Namibian territory. And so surface water resources are intermittent and so very hardly accessible. And furthermore, groundwater is mainly saline and is also not available for drinking water supply. And this leads to the fact that there is a high dependency on external water resources. So in our case, in central northern Namibia, fresh water is coming from Angola or the Angolan-Namibian border river Kunene. And by a 150 kilometers long open canal, fresh water is conveyed into the region. And one fact that is, I guess, very important to know is that almost half of the Namibian population is living in central northern Namibia. One reason might be more historical. So the ethnic group that is living there has been living there for a long time and is able to do livestock farming and rain-fed farming in this region. And the other reason is water supply. So there is drinking water supplies by a large technical infrastructure, not only this 150 kilometers long open canal, but also a pipeline network of, I guess, more than 2,000 kilometers of length in total, which makes sure that drinking water can be supplied to the population. And factors that exacerbate the situation are, first of all, that there is growing water scarcity due to population growth on the one hand, and the other aspect is climate change, of course. And population growth does not only apply to the overall numbers of the population, but also in terms of where is this population located. So there is a high process of urbanization going on in this region. And climate change, what I've mentioned before, will lead to increased droughts. That is what we can already observe. And on the other hand, the number of heavy rainfalls will rise as well. So we have on a regular basis already flooding of the whole area of northern Namibia. And if we take a closer look at the town of Utapi, at the time of the last census in 2011, 7,000 inhabitants were counted. And from our perspective, nobody knows exactly. I would guess it is way above 10,000 people living in this town by now. And I've told you about the drinking water supply, and in terms of the wastewater infrastructure, we have in this town mainly gravity sewers and so-called waste stabilization ponds. I will come back to this infrastructure later in the Epona project. So what do we do about this situation, this hydrological situation, but also this social setting? So our solution, or our suggestion for the solution, would be that there should be a diversification of water resources, and the main means for that would be water reuse. Okay, let's go right into the first project. It is a research project called Kuwe Waters, which has been funded by the German Federal Ministry of Education and Research. This project ran for almost 10 years, from 2006 to 2015. And the project partners are the Darmstadt University of Technology and a couple of industry partners, one of them being Acceptance. What is Kuwe Waters about? So within Kuwe Waters, several technological options were tested. I won't tell you about rainwater harvesting today. I won't tell you about solar groundwater desalination today. What we are focusing now is water reuse for irrigation agriculture. And this system has been set up within informal settlements of Utapi, which have not been equipped with any kind of water infrastructure yet in terms of wastewater. So three kinds of different settlements were supplied with wastewater infrastructure. We have a so-called wash house that supplies informal houses or inhabitants in this informal settlement. Then we have so-called cluster units. I will show you some pictures and more facts and figures on these cluster units later on. And then the shack dwellers, which you can see here. This wastewater, this municipal wastewater, is conveyed through a vacuum sewer system to a water reuse plant, which I will also show you in detail later on. And finally, we can produce irrigation water, which is stored in a pond and which can be used for, let's say, horticulture, for producing fruits and vegetables for human consumption.
Can you briefly comment on why a vacuum system?
Yeah, that's a good question. You need to know that the floodings that I've mentioned are really on a regular basis. So we have a distinct rainy season each and every year, and it might not be that in every year the whole area is flooded, but let's say every second year or something like that. And this poses huge risks to the existing wastewater infrastructure, which is a gravity sewer and a waste stabilization pond outside of the town, which is flowing over on a regular basis, so posing risks for environment and the people. And one way to make it flood-proof would be to find out whether vacuum sewers might be the right choice. The other aspect which comes into mind maybe at first place is that, of course, you save water for flushing the feces, but that is, from my perspective, that is secondary in terms of why we tried vacuum sewers. All right, this is some impressions on the different parts of the system. So we can see here the communal washhouse. Let's skip this to later to tell you more about what this washhouse is able to do. We have this reuse facility, and you can see from the title of this slide, this reuse facility is named after a former CEO of the town council, Oswin O. Namakalu. And then you see an impression of the irrigation fields and then a photo from the greenhouses that are supplied with this reused water. But I will go into detail of all of these stages of the system. So let's start with the informal settlements. As I've mentioned, the communal washhouse can be used publicly if you pay a fee to use it, and there are toilets, showers for the population of this informal settlement, which don't have any access to wastewater infrastructure. And this washhouse has been designed for a number of roughly 150 users per day. And what you can see here is that they also can wash their laundry, which is another option in terms of this communal washhouse. The so-called cluster units are facilities which have a toilet and a shower and also a basin for laundry washing, which is shared by, 3 to 4 households. And in total, 30 cluster units have been erected. And so 40 people are served with these cluster units. And finally, this is not anymore the poorest of the poor. What I would say about this informal settlements where the communal washhouse has been built, but this is, let's say, the lower middle class, which are able to afford themselves single houses, brick houses, and these shack dwellers were also supplied or connected to the vacuum sewer system. And in total, it has been 55 households, and which makes 240 users as well. Now, this is a layout of the technical scheme of the reuse facility. And as you can see, we see here the municipal wastewater, the vacuum station, and the treatment steps that are applied are, first of all, as you can see, that there are 2 lines. Both are identically equipped. And we have, first of all, as a anaerobic treatment step, a so-called UASB, upflow anaerobic sludge blankets. We have as an aerobic stage rotating biological contactors, clarifiers, and then a microscreen or microsieve with a mesh size of roughly, if I remember correctly, 15 micrometers. And after that, a UV disinfection. And after that, the reused water or reclaimed water is stored in a storage pond and then provided to the irrigation site or the horticultural site. Things I'm not going to focus on today is that, but I don't want to not mention it, that the biomass from the agricultural side is a co-substrate together with the sewage sludge and is conveyed to a fermenter where digestion takes place, and we can produce biogas. And together with the biogas from the UASBs, electricity is generated. Potentially 1/3 of the energy demand of this plant. But I will tell you later on what the technical problems with the fermenter were that we never reached this goal. And I want to stress this again. These technical aspects were under the responsibility of our colleagues from the Darmstadt University of Technology. So this is not ISOE's expertise, but I want to present to you, of course, the whole system so that you can see the context. Yeah, the irrigation agriculture, the fields have a size of roughly 3 hectares in total. So this is why I'm talking more of horticulture. And we calculated with roughly approximately 35 cubic meters per hectare and day. So the capacity of our reuse facility has 90 cubic meters per day of wastewater. And the crops produced are high-growing crops, tomato, green pepper, maize, watermelon, pumpkin, and the harvest, the potential harvest is approximately 32 tons per hectare and year of fruits and vegetables. Some technical specifications. First of all, the water is tested for being hygienically safe for this reuse purpose. I will show you the multi-barrier approach later on. And one advantage, of course, of this kind of water reuse is that nutrients, especially N, P, and K, are left in the water, so they contribute to fertilizing the fruits and the vegetables that are produced. The pond has a capacity of roughly 4,000 cubic meters to be able to buffer fluctuations between inflow and usage on the irrigation side. We have high tanks in total of 70 cubic meters and with a pressure of 0.6 to 0.9 bars to be able to supply a drip irrigation system to minimize water losses. And here again, you can see some impressions from the farmers or the workers on the fields and from one of the greenhouses. Yeah, this is the multi-barrier approach that I've already mentioned. And the barriers consist of, first of all, the sanitation facilities themselves, because we avoid, of course, any kind of open defecation. And then the treatment plant, of course, is a barrier, the storage pond, the drip irrigation system, and the fruits themselves, if they're not getting in contact with the reused water. And as you can see from our observations and our measurements in terms of E. coli, rotavirus, and hookworm eggs, we can see a considerable reduction of these pathogens in terms of E. coli to 0.02, in terms of rotavirus to the 10 to the power of -7, and hookworm eggs are not detected after the treatment plant due to the microscreen that is applied. I will tell you some insight about the technical problems and challenges with such kind of treatment as well, why I am stressing that this depends on the microscreen working, that there are no hookworm eggs. Yeah, these technical measures, as you have mentioned at the beginning already, are always accompanied by, let's put it like that, social and other innovations to be able to realize the complete concept of water reuse. And in this case, I want to focus on the so-called community health clubs that we also developed and designed. And these community health clubs are established to promote safe hygiene practices within the informal settlements among the users. There are some initiatives also in terms of the technicians and the managers within the operator side, but I'm not stressing and focusing on that now. And these trainings and educations, they helped educate the residents, and there are a number of benefits connected to this kind of training measures. At the end, it contributes to reducing health risks and any kind of risks that are associated with any kind of poor sanitation. So one notable impact that we were able to prove through two surveys, rather at the beginning of the setting up of the system and at the end of our project, 2012 and 2015, here mentioned here, is that there is a significant drop of, first of all, diarrhea cases, and secondly, also the open defecation rate has significantly dropped. But of course, this is just a side project of our big technological project. Such things can be made, or you can make a whole project out of this study alone. So I'm not going to stress any further on this topic. Yeah, I've mentioned the technical challenges already. So the major technical challenges that we observed were, first of all, you need a thorough supervision of the required, or a thorough supervision is required throughout the whole construction phase. This applies, for example, to subcontractors. This applies, for example, to what kind of materials are used for the vacuum sewers. Is the subcontractor welding these pipes correctly? So we had issues even at the construction phase, but finally this could be managed and the system was working. But if we knew that before, we could have avoided some time or some delays within the project. Secondly, energy recovery from sewage sludge and biomass was not fully implemented. And this has simply technological reasons. The supplier of this fermenter was not able to get certain spare parts to get the system running. This is one aspect. The other aspect is that we never reached full capacity of our reuse plant. So these 90 cubic meters per day were never reached. So at the beginning, it was roughly 1/3. And during the course of the project, we reached roughly 1/2 of this capacity, leading to a much lower amount of sewage sludge, and also in terms of the irrigation side, of course, in terms of co-substrates from the irrigation agriculture. And it was simply not working like we assumed it would work. One other aspect in terms of the vacuum sewers is that there's problematic material within the vacuum sewers that were constantly destroying the vacuum pumps for a certain period. And there are certain stones of fruits that are very commonly eaten in this region, the so-called amber fruit. And these stones simply destroyed the vacuum pumps. So we needed to install, after we have identified what the problem is, we needed to install a facility to remove these stones beforehand, before it gets to the vacuum pumps. And furthermore, the number of users and water quantities were overestimated due to unpredictable population dynamics. This is exactly what I've mentioned already in the context of the fermenter. So the sanitation and treatment facilities were oversized, and there is less water and nutrients for the irrigation. So after the project, to not leave you with this kind of information, after the project, we made sure that the operator, which is the local authority, started thinking about connecting other wastewater pumping stations to our system to get more municipal wastewater into our system to bring this reuse facility to its full capacity. And we are until now still working on connecting further pumping stations. The current status and some benefits I want to mention with regard to this plant is start of operation was in 2013. This plant was handed over to Utapi town in 2015, and this plant is still running up until today. And this is mentioned in the next bullet point. Vacuum sewer system and reclamation plant is functioning reliably. Another success, I would say, is that the sanitation facilities were well accepted and are still in use until today, and they are very well maintained. There is a high level of commitment from the side of the Utapi town council throughout the whole project, and I think that's a major factor why such a system is still running. And furthermore, technical skills are sufficient for operation and maintenance tasks, especially with view on the technicians that are needed to run such a system. So these technicians have been trained during the project, and they are still able to repair and maintain the system. Some ecological and social benefits I want to mention is, first of all, of course, we have a improved water use efficiency in a very water scarce region. So Namibia is one of the driest countries in the world, and this contributes to water security, at least on a local scale. There are several full-time and part-time jobs created. Just one example are the technicians that I've been mentioning. And then furthermore, we have a reduced open defecation rate and improved hygienic conditions in the settlements. So the health status of the inhabitants has been increased by less diarrhea cases, for example. And finally, of course, due to the fact that crops or fruits and vegetables are produced for human consumption, there is also a contribution to food security through such a project. That was case study 1. Case study 2 is the so-called EPONA project. So this project is also funded by the German Federal Ministry of Education and Research, and it ran from 2016 up until 2020. And while the Kuvu Waters project was setting up a whole new infrastructure, as you have seen, with the vacuum sewers, with the reuse plant, EPONA took advantage of the existing wastewater infrastructure. This is one thing that we thought should be tested in another project. And as I said, gravity sewers and also waste stabilization ponds are used to get rid of the wastewater in Utapi. So wastewater is collected from central parts of this town to these ponds that are lying outside of Utapi. And I can show you some satellite images. These are the ponds. Let me just quickly tell you, or I will do that on the next slide, what pond is which function it has. So the design in 2004 was that these ponds were constructed for 2,000 to 2,500 inhabitants. And there are 2 parallel lines with 4 ponds each. So this is line A, pond A1, A2, A3, A4. The first pond is a facultative pond, and then followed by 3 maturation ponds. And then there is a second line B, with 4 ponds again. And then a so-called evaporation pond has been added. The evaporation pond has a surface area of roughly 40,000 square meters, which is more or less the same surface area as all of the ponds mentioned before from line A and line 2. But as you can see already, the status quo in 2016 when EPONA started is that more than 5,000 people are connected to the system. And up until now, I would say out of the approximately 12,000 inhabitants, maybe 7,000 are connected to this pond system. So it is far beyond the capacity of these ponds. and which also contributes to these ponds for overflowing. And so the main challenges connected to such kind of infrastructure is that, oh, I don't want to leave that out. This area here is the area for the agricultural irrigation. I will tell you more about later. So the challenges of these kinds of wave stabilization ponds are, first of all, of course, the dimensioning. The filling capacities do not correspond to rapid population growth. Furthermore, wastewater ponds are frequently overflowing, especially during the rainy season. And then apart from that problem, we have an inadequate maintenance and cleaning of the ponds. So the sludge that settles down in these ponds should be removed on a regular basis, which is, of course, not taking place. So these ponds run year after year and fill up with sediments and sludge, which is a problem for functionality of these ponds. Furthermore, we have vandalism to the ponds and also to the fencing. The reasons for these kinds of vandalism is one aspect is fishing. There are fish living inside these ponds, so people are coming to fish and catch these fish. And the other aspect is watering cattle or any other kind of livestock. So people break the walls of these ponds deliberately to get access to the water to water their livestock. And apart from all these practical problems, of course, there are problems in terms of the allocated budgets, which only cover the operation. But of course, it is not possible to finance any reinvestments or expansions of these kinds of ponds. So yeah, this leaves you with, in financial terms, with no options to adjust the situation to the needs of the population growth. And furthermore, there is a lack of know-how for water reuse potentials. This water reuse does not play any kind of role with regard to operating these kinds of ponds on a regular basis. And finally, there is an inadequate organization and emptying of private septic tanks. I might come back to this challenge later on. I will leave it out. So this is again an overview over the technical measures that we undertook. And again, I want to stress the technical parts are under the responsibility of the colleagues from Darmstadt, from the Technical University of Darmstadt, and our industry partners. And in this case, it was Acceptance. And first of all, there is a pre-treatment before the wastewater enters the ponds, and we tested two kinds of pre-treatment steps. One again is UASB, the upflow anaerobic sludge blankets, and the other one is using microscreens, but in this time a drum screen with a mesh size of 250 micrometers. Furthermore, we improved the flow within the ponds by installing guiding walls. So this improves or optimizes the retention time, the flow through these ponds. And finally, a post-treatment step is a rock filter installed within the last pond, A4, and a rock filter which makes sure that, for example, algae are removed. And finally, we are able to produce irrigation water, but in this case, because there is no disinfection and complying to the Namibian Code of Practice for water reuse, only fodder crops for livestock can be produced by such a way, and only considering certain kinds of irrigation techniques. I forgot to tell you also about one other improvement. You can see here in this satellite image, it was this picture was taken right at the moment when we cleaned the first pond from sludge, and this is why you can see it is empty. So improving the functionality of these ponds is not only connected to these guiding walls that were installed, but also in terms of removing the sludge. Here again, we have a technical layout, and let me see what I have not mentioned before. Maybe it is interesting for you to see what we did with the pretreatment. So here is the pumping station where the municipal wastewater is coming in to this pond system. We have the UASB and the microscreen in parallel lines, so we were able to compare these two kinds of pretreatment, and then this pretreated water enters line A. You can see the guiding walls and the rock filter in the last pond, and line B was left as is to be able to compare is there any kind of improvement. And after that, there are high tanks in the irrigation side. And what is interesting for you is also that since both of these pilot plants for water reuse are also both located in Utapi, of course, we were able to make connections between both of these plants. And so the sludge from the microscreen was conveyed to the fermenter that I've mentioned before at the Oswin Namakalu plant. And since the UASB is not treating as much or not potentially able to treat as much water as the microscreens, this sludge is only dried in drying bed. And unfortunately, since due to the distance between two plants, the biogas from the UASB is only flamed, I guess is the right English term, with a torch. Some impressions on the irrigation side. I won't go into too much facts and figures. These studies on the irrigation are under the responsibility of our colleagues from Geisenheim University. And for example, first of all, we tested different kinds of irrigation technology or irrigation techniques. Furrow irrigation, as you can see here in the left image, drain irrigation in the middle picture. Drain irrigation is more or less using drain pipes and irrigating the crops also subsurface. And finally, on the right-hand picture, you can see drip, classical or conventional drip irrigation systems. And here are some impressions of the crops. What you can see here is sorghum. And the colleagues from Geisenheim University tested sorghum in comparison to alfalfa or lucerne. I will tell you only briefly about the results of these studies as well. But first of all, in terms of technology, what are the conclusions and the results? So first of all, the measures for treatment, for pre-treatment that were taken, they reduce the chemical oxygen demand and also total suspended solids. And the UASB furthermore reduces dissolved COD and also pathogens and nutrients in the wastewater. Furthermore, the effluent quality of the upgraded line is significantly better than the one that has been left as it was before. So in terms of chemical oxygen demand, there is a reduction of 27% or in comparison to the line B. And in terms of nitrogen, minus 27. In this case, you might argue, of course, it is desirable to keep nitrogen in the water because it is used for irrigation purposes. And finally, also in terms of E. coli, we observed a reduction of minus 70%. And yeah, the reuse of water and nutrients for irrigation of fodder plants is possible through such a technology. It complies with the Namibian Code of Practice for Water Reuse, which allows you not to use disinfection for the production of fodder crops, as I said. And furthermore, the results in terms of the irrigation and plant production is that furrow irrigation is the cheapest, which is kind of obvious, but the best yields were achieved with drain irrigation. And in terms of the comparison of sorghum and alfalfa, the result is that we achieved better yields with sorghum. Yeah, these were more the technological and let's say agricultural results. Again, this is what ISOE has been contributing to accompany these kind of technical and social innovations. And this is what we call a wastewater treatment plant partnership in northern Namibia, because we thought and we learned from the experiences in Kuva waters that focusing only on this one location might be good for this one location, but it doesn't change anything on a bigger scale. And this wastewater treatment plant partnership is a network of 13 local authorities in northern Namibia and 5 regional authorities. And core towns are, of course, Utapi, but also, just to mention them, Okahau and Oshokuku. And yeah, what is the purpose and what are the advantages of such kind of a partnership? First of all, this network serves to exchange knowledge and experiences among the participants. So this applies, for example, to improve pond management. And furthermore, we can identify options for sharing financial, personal, or technical resources. So not each and every local authority needs to have a device for checking the sewers or something like that. Or you can think about, for example, which kind of supplier for pumps and spare parts are hired. This also refers to the last bullet point. You can create a stronger bargaining power vis-a-vis negotiation partners, for example, consultants, suppliers, authorities, international organizations. But of course, this also applies to the local and the national scale. So you have another weight in terms of mentioning your challenges in municipalities and local authorities against the national ministry, which is another advantage. I skipped one aspect, and this is a better communication between regional councils and local authorities. So it simply improves the wastewater management in general if there is more communication and if there is such a network installed. To give you an impression, we were able, during the runtime of 3 years of IPONA, we were able to organize 6 meetings of this partnership, and the topics were ranging, that were discussed during these meetings were ranging from general wastewater management in local authorities to what are the potentials of water reuse. One important aspect was joint procurement, so how can local authorities jointly procure services against suppliers and companies, which gives them much more power to bargain and to not be dependent on certain spare parts, on certain types of technology. And finally, we also took advantage of the opportunity to talk about very practical things like pump repairs, pump maintenance, but also understanding basic water quality parameters and stuff like that. This is the side of the contents, and in terms of the institutionalization or formalization of such kind of network, what we did is we set up a memorandum of understanding that all the participants signed during the course of the project, and we had a body, a steering committee at the end that was able to organize these meetings by themselves and to set the topics that were exchanged within this partnership. Yeah, that's it so far with regard to these 2 examples. I see that the time is running, so I have to hurry up a little bit. What are our current activities? So let me take a quick look at my notes to frame this best. Both presented reuse examples are examples which are very locally limited. Those are local pilot plants. So we thought of what would that mean if we bring these kinds of ideas on water reuse to a national scale, to a nationwide scale. And this is what we are doing, or what we have been doing just until now in the project Varenam, again, a German research ministry funded project. And the partners, I want to mention them before again, and I have mentioned them before, are the Darmstadt University of Technology. I want to mention also the Emscher Genossenschaft, the biggest wastewater company in Germany. Several industry partners that are involved, and on the Namibian side, because even though they have been a partner in our previous projects before, the Ministry of Agriculture, Water and Land Reform is certainly the main actor on the Namibian side when we are speaking of nationwide initiatives. And yeah, what we think is that the diversification of water resources with a special view on water reuse is a promising solution to deal with these kinds of challenges that I've already explained to you. And we argue that there is a huge untapped potential for water reuse, since each and every local authority of a medium size has these kinds of wastewater ponds or waste stabilization ponds. And so there is a huge potential for water reuse and relieving the stress from the drinking water supply and contributing to water security. And the overall goal of Varenam is to develop a joint national water reuse strategy for Namibia to increase water security in Namibia. And we had an initial phase up to now, which can be defined as the co-design phase, where we designed the project outline with the Namibian actors, mainly the ministry. And as you can see here on the right-hand side, we have organized the projects according to a transformation management approach. So we were looking at what kind of system knowledge do we need to assess the problem situation, what kind of orientation knowledge can we jointly produce with our Namibian actors to find out what are desirable and sustainable future scenarios of water reuse in Namibia. And then finally, transformation knowledge, what kind of options do we have and which of these options are more costly or less costly, which contribute more to sustainability or sustainable development. I will keep it with that. And concerning the time, I think I will make this very brief. So we are focusing on several multiple spatial scales. We are looking at larger cities or municipalities, such as Walfish Bay, which will be a place for a pilot plant for industrial water reuse. And we are using differently from the projects presented to you before, for example, membrane technology to produce surface water. In this case, since Walfish Bay is involved in many endeavors with regard to green hydrogen production, there is a connection even to the recent discussion on maybe it is possible to use reused water for green hydrogen production in Walfish Bay. And then larger towns such as Oshakati, which are equipped with waste stabilization ponds, they might be a role model for irrigation agriculture with the technologies that I've presented to you. And then there are medium-sized towns which might be part of a nationwide network of local authorities and regional authorities to make this water reuse strategy real. Main components are technology, governance, and capacity development. So we are asking what kind of technology do we need to implement such a water reuse strategy? What kind of institutions and governance do we need to realize the reuse strategy? And what kind of capacities are needed on a management level, but also on a technician's level to realize this strategy? And to just mention a few of these benefits, we argue that this is a contribution to diversifying water resources in Namibia, which is important for the water security in Namibia, with the argumentation that water reuse is certainly better than letting the precious water evaporate in wastewater ponds. So we want to replace evaporation through evapotranspiration through plants. At the end, the same effect, and we are avoiding overflowing of the ponds, and we are also contributing to food security. And let's come also to the last point. Maybe Namibia could be a role model for other Southern African countries in terms of water reuse. Conclusions and success factors. Then I will conclude my talk. So first of all, what are the lessons learned? First of all, a well-adapted implementation through demand-responsive approach is important. This applies mainly to an early involvement of stakeholders and an establishment of community health clubs, for example, within the Epona project was important to the implementation of the management systems around it. And then future capacity development needs to focus on operators management skills that can be improved. And one problem might be supply chains and availability of spare parts. This is with regard to the UV disinfection in the Kubu Waters project, because we really had bottlenecks of being able to get a grip on UV lamps to be able to run the UV disinfection. And another thing is that informal partnerships reach their limits when institutionalization and support from higher governance levels are insufficient, which is the case with the wastewater treatment plant partnership. We notice that if there is no backing from the national level, from the government side, then these kinds of partnership are highly dependent on the people that are working in there and supporting this network. And yeah, funding of investments is a major challenge. Furthermore, the allocation of responsibilities between the operator and the farmers in the irrigation schemes. And last but not least, the farmer needs to have a lot of business experience on the one hand, and on the other hand, also agricultural knowledge, which is kind of a challenge to find such kind of small-scale farmers in northern Namibia. My last slide, what are success factors? So first of all, the development of trust and confidence among all involved parties. This applies mainly to considering the demands of the partners in Namibia for the project formulation. Furthermore, the combination of technological and social innovations. If we only look at the technological innovations, of course, these projects are deemed to fail. So only by doing or by looking at both of these aspects, we are able to have a sustainable institutionalization of operation and management. Thirdly, the promotion of capacity development and the multiplication of proposed technologies. This is, I think, the main instrument to bridge the gap between research and practice. Otherwise, it will stay a research project and won't be able to have an impact on solving societal problems. And finally, you need flexible thinking, which is not attached to linear planning. So one example is conflict management that has to be done on an everyday basis. And the other aspect is you are not, if you stick to your proposal, the project is going to fail. So you need the flexibility to steer away from the things that you have thought of at the beginning. Yeah, I hope I have sparked some interest in our projects, and I'm looking forward to any kind of questions, comments from your side. I want to thank at the end our project partners that I've mentioned already, our funders, the German Ministry of Education and Research, our project partners, the Darmstadt University of Technology, the University of Geisenheim, the Emscher Genossenschaft, our industry partner Acceptance, and first and foremost, our Namibian partners, with special focus on the Namibian Ministry of Agriculture, Water and Land Reform. And that's it. Thank you very much for your attention.